Alright, so our second section in regards to chapters 2 and 9 deals with physical and chemical changes. When you hear physical versus chemical changes, you should understand that physical doesn't change what the substance is. Chemical change does change indeed what it is. Physical change is when some properties of a material may change, but the composition, what it is, does not change. So an example, breaking, splitting, grinding, cutting, crushing, ripping. If you rip a piece of paper in half, you certainly have a different appearance, but the composition does not change. Splitting, grinding, cutting, ripping. Also, physical changes: boil, freeze, melting, condensing. If, as we just saw in the last video with the distillation, water changing from liquid water, if I would have had frozen ice and went from the ice solid state to the liquid, then heated it up to the gaseous state, all those changes are just physical changes. It's still H2O, still water, steam, ice, H2O. So those physical changes, boiling, freezing, melting, are all descriptions of that. Chemical changes when a change that produces matter with a different composition than the original matter. So those examples, of course, would be things like burning, rotting, rusting, decomposing, exploding, corroding. A perfect example, of course, is rusting. If we look at iron with oxygen, obviously iron and oxygen getting together are going to have rust if you have iron exposed to oxygen, and you'll form that Fe2O3. This right here would deal with rust. It's no longer iron, it's now rust. So that's an example, of course, of a chemical change. I know you're happy to hear and see different things like exploding, corroding, but additionally, I do want to mention that the law of conservation of mass. In any physical change or chemical reaction, mass is conserved. Mass can neither be created nor destroyed. So whether you've got a fire and you're burning something, certainly you have a chunk of wood that has a certain mass. When you burn it, there's going to be something apparently missing. Well, there's really nothing missing. You can't create nor destroy mass. There'll be ashes that have mass. There'll be some soot or smoke that goes off. That smoke has particles. There's some mass in there. And so it may have changed forms, but it still has the same mass. I do want to now quickly look to moving this next chapter here, if we deal with kind of the old periodic table of elements, and I do want to take a look at that. So the periodic table of elements. This is where we kind of can move into a little bit of the chapter 9 stuff. Periodic table of elements, obviously on any periodic table there's going to be symbols. You're going to have Na, Cl, Pb, the symbols themselves. In addition, you'll have whole numbers, which is the number of protons. So if you look at the periodic table that we have in our room, there's the symbols. Above that to the top, you have the atomic number, which is the number of protons. Those are the whole numbers, 1 through 113, 112. The other number, the one with the decimal, is the atomic mass. These are the basic, I say atomic mass, it's not necessarily the mass number, because those mass numbers are usually whole numbers, but we do have our atomic mass. All right, here's what your periodic table looks like, and I just showed a quick little periodic table. This is a nice little description. Here we have different colors that show different representations of things. For example, the blue ones over here are your alkali metals, alkaline earth metals. These yellow ones here in the middle, your transition metals. We have our noble gases, etc., etc. So we have different colors to represent different things. Certainly periodic tables have may have more or less descriptions as well. If we look now to this periodic table, there's the element song. I'd like to see if we can play that right now. Get a little song. All right, so this is a good one right here. Tom Lehrer.
There's antimony, arsenic, aluminum, selenium, and hydrogen, and oxygen, and nitrogen, and rhenium, and nickel, neodymium, neptunium, germanium, and iron, and lycium, ruthenium, uranium, europium, zirconium, lutetium, vanadium, and lanthanum, and osmium, and astatine, and radium, and gold, protactinium, and indium, and gallium, and iodine, and thorium, and thulium, and thallium. There's yttrium, terbium, actinium, rubidium, and boron, gadolinium, niobium, iridium, and strontium, and silicon, and silver, and samarium, and chrysoprome, lithium, beryllium, and barium. There's holmium, and helium, and hafnium, and erbium, and phosphorus, and francium, and fluorine, and terbium, and manganese, and mercury, and aluminum, and magnesium, and dysprosium, and scandium, and cerium, and cesium, and lead, praseodymium, and platinum, and plutonium, palladium, potassium, potassium, polonium, and tantalum, technetium, titanium, tellurium, and cadmium, and calcium, and chromium, and curium. There's sulfur, californium, and fermium, berkelium, and also mendelevium, isonium, nobelium, and argon, and thorium, and radium, and rhodium, and chlorine, copper, 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 tungsten, tin, and sodium. These are the only ones of which the news has come to Harvard, and there may be many others, but they haven't been discovered.
So obviously a nice little periodic table song. You're obviously going to recognize and know most of those. I don't want to say that we're going to memorize those elements, but certainly we're going to be expected to know them pretty well.